Good morning, dear students. This is Determinant part 13. In the previous part 12, we discussed about the concept that is adjoint of a given matrix A. We solved some examples also. Now, by using that adjoint of a given matrix A, a very good theorem is there. This is very important theorem. You follow it well. Okay, now? What is the statement of the theorem is? So that A into adjoint A into adjoint A is equal adjoint A into A, that is equal to det A into I. Suppose A is a matrix, a square matrix of any order, 2 by 2, 3 by 2. That A into its adjoint A. Its adjoint. Adjoint is one concept. That is replacing the elements of the given matrix and we refill its corresponding cofactors and then we transpose. That is adjoint A. Already we know it well. With that adjoint A, if you multiply A, we get that A into I. Or adjoint A into A. Computed law is there. 5 into 6, 6 into 5, just like. It gives the same answer. That A into I, where I is a unit matrix, identity matrix. Now, we'll go to prove this one. Here, let capital A is equal to a general matrix. I am taking a general matrix. A11, A12, A13, A21, A22, A23, A31, 32, 33. Here A is common. With only a single variable, we are expressing the 9 elements in the 3 by 3 matrix. But the position is 1, 1 means first row, first column. 2, 2 means second row, second column. 3, 2 means third row, second column. Like that. That is A. And what is adjoint of A? The same example is given there in the previous 12th part. Adjoint of A. For A11, capital A11 is a cofactor. Instead of A, small a11 element, I am writing I replaced by its corresponding cofactor. A12 here is there, but I wrote A capital A12 here. Row will become as a column. Again we have to transpose. A31 capital A13 is there. Again A21 A22 small letter capital A22 A23 capital A23. This is row and it is column. Of course, we are taking out the elements and in the place we replace its corresponding cofactors. And then we transpose. So this is adjoint A. Yes? Okay. Now, A into adjoint A we are considering. A into adjoint A we are considering. A is the matrix is given. Adjoint A we found that is there and now we are multiplying. Row into column. First row, first column. First row, second column. First row, third column. Like that A11 into capital A11. Okay na? A12 capital A12. Okay na? Row into column. That is the method to multiply the matrix. Again A13 into capital A13. It is working. A11. Again, this is only one element. Multiplication is the row, first column. That is first element. First row, second column is the second element in the first row. First row, third column elements. That is the third element in the first row. Like that. You know it well. A11, A, that is A31. A12, A32. A13, A33. Yeah. Again, we are going to take the second row, first column. Second row is A21, A11, yeah. A22, A12, that is A23, A13, yeah, this is okay. Again, A21 is there. It is important. A22, capital A22. A23, capital A23. This sum of product is a different one. If you observe this one, we can. Here also, the last, third row, first column. Third row, second column. Third row, third column. A31, A31. A32, A32. This is 32. And A33, capital A33. Yeah. It is also a different one. You see, here in the diagonal, it is a matrix. 1, 2, 3, 4, 5, 6, 7, 8, 9 elements are there. In the diagonal, you see, this sum of product, you see, A11, capital A11 is there. A12, 1, 2, A13, 1, 3. Here also 2, 1, 2, 1, 2, 2, 2, 2, 3, 2, 3, 2, 3. There 3, 1, 3, 1, 3, 1, 3, 2, 3, 3, 3, 3 is there. What about the remaining elements? They are not in the same. Here capital A11, small a11, but capital A2. You see here, it is a different not corresponding cofactor. The A11 is multiplied by another cofactor, another element cofactor. A12, but A22 is there. What I want to tell, you see, here what is the meaning? This is sum of product of the elements, these elements, multiplied by their corresponding cofactor. That is det A. It is simply det A. Whereas this one, A11, A12, A13 is the elements, but it is multiplied by another element's cofactor. So it is 0. The property is there. This is 0. And here also it is 0 because A11 it is A31. If it is same is there, it will become as a determinant. You see here A21, A21, A22, 22, 23, 23. Whereas the remaining are different. Element is okay, sum of elements, but multiplied by not corresponding, a different element corresponding cofactor. So it will become as 0. But this one and it is and the last one, they are det A's. Okay now, you catch that one, that property, det A, det A, det A. This is det A, this is det A. It is det A. It is also det A. It is also det A. The remaining is 0. It is 0. It is 0 and it is 0. It is 0. Okay now? Like that we will get. Now, it is a matrix. 9 elements are there. In the 9 elements, det A is a common. So I took det A as a common. Det A of 1, there remain 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay now, this is nothing but det A into I. What we took A into adjoint A. A into adjoint we consider. That is equal to, at last we get det A into I. Similarly, we can prove adjoint into A. If you take this one is there and it is next term. If you take like that, we will multiply in the same method, we will get det A into I as it is. Hence, we get A into adjoint A is equal to adjoint A into A is equal to det A into I. That is what we require to prove. That is the theorem ends. Okay. Here, one more thing I want to tell. There is a notice there. Since what I proved, A into adjoint A into A is equal to det A into I now. That det A is a number. I am saying, not a matrix. I is a matrix. Here also there are matrices. But det A is a determinant of a matrix is a number. That number will be goes that side. It is multiplying, here it is dividing. 1 by det A into adjoint A. 1 by det A into adjoint A into A. I am writing in some order. A into 1 by det A, that det A divided here. 1 by det A into adjoint A. 1 by det A into adjoint A into A. You see, Here, how it is, A into B is equal to B into A is equal to I. Okay, na? Here, I remains. A into B is equal to B into A is equal to I means invertible matrix. A matrix is said to be invertible means it is containing inverse. Any, if another matrix B is existed, A into B is equal to B into A is equal to I, then B is called inverse of A, like that. Here this part, this part is B. That is nothing but inverse of A. Will you agree? This part is just like B. It is inverse of A. So A inverse notation I read. A inverse is equal to nothing but 1 by delta A into adjoint A. It is two concepts are there very important. By using this one, we can find the inverse of any matrix. Okay, na? This is very important theorem. Try to follow it 3 or 4 times. You will learn it well. Okay, na? Yeah. Okay. The second property. This is theorem, but this proof is not needed. But as a knowledge purpose, you learn it. Okay, na? In the textbook, this theorem is not asked, but a statement is there. AB whole inverse is equal to B inverse into A inverse. The same concept is taught in transpose of a matrix. AB whole transpose is equal to B transpose into A transpose. Like that here also. Okay, now? There the proof is there. But here, the question will be asked, verify that AB whole inverse is equal to B inverse into A inverse by taking 2 examples, or otherwise they will give in the exam itself. A is equal to a 2 by 2 matrix, B is also a 2 by 2 matrix, and we have to verify that one, or 3 by 3 also. But it is for our knowledge purpose, I am giving the proof. Okay, you see, observe me. Here, in order to prove it is AB whole inverse, it is reversed B inverse, A inverse. Okay, now suppose A, B, C whole inverse is there, C inverse, B inverse, A inverse, like that. It is reversed. Here, consider I am taking a logical proof. B inverse, A inverse into AB. I am taking one expression. B inverse, A inverse, AB. It is brackets in some different way. By using the associative law. Associative law means product is same. B inverse, A inverse, A, B. But brackets are different. I am taking the brackets only for A inverse into A. But order is same. The brackets we are taking in a different way. That proof is there, that property is there, that statement is there in the previous associative law for the product, for the multiplication of matrices is there. So A inverse into A, I am putting in one bracket. A inverse into A is I. So this is I. Okay, na? B inverse, this is I into B. IB is nothing but again B. Okay, na? We will put it in one bracket. IB means any matrix multiplied by identity matrix means it is itself. So B inverse into B. Again we get I. So what we proved, what we considered, B inverse, A inverse into AB is equal to I. Okay. Similarly, if you take AB into B inverse into A inverse, you see A, B inverse put in one bracket. That A inverse is separated. Okay, na? Now it is A, this is I. Okay, na? As usual. I. And I is nothing but A. A into this A inverse. Again we get I. What we consider in the secondly, AB, B inverse, A inverse is equal to I. Okay, na? By using, say this is 1 and it is 2. From 1 and 2, answer is I same. So here it is B inverse, A inverse into AB. Or take this one. Whatever it may be. second part, and this is the first part I wrote, and I is equal to I. Same. Okay then. That means x into y is equal to y into x is equal to I. By using the concept of inverse matrix. This is the inverse of this one. X into y. Y into x is equal to I means y is inverse of x. This part is inverse of this one. Same I wrote this one. B inverse A inverse is inverse of A. That means notation AB whole inverse is equal to B inverse A inverse. Okay then? That is proof. Okay then? Like this you learn it. It is only knowledge purpose. This may not be asked in the exam. No need to by heart it. If interest is there, you learn it. But this concept is very important. We are given two matrices and we have to verify whether it is correct or not. Okay na? Like that. Huh? Yeah, proof. Okay then. The concepts totally it is completed. Now we are going to find the 4.5 exercise, fifth exercise. This exercise is important. First, solution. We have to find the adjoint matrix. Given, what is given? Given A is equal to, it is 1, 2, 3, 4. We have to find the adjoint here. First find cofactor. Cofactors of 1. Cofactor of 1 is, what is the cofactor of 1? You delete row and column, we get to 4. That is plus 1. Plus, okay na? Minus. Okay na, like that. Cofactor of 2. The row and column is deleted. It is 3, but minus 3. Be careful. Okay na? Again, cofactor of 3. It is also minus. Plus, minus, minus, plus, like that. For 3 matrix, for 3 element, the cofactor is to delete this one and 2 is there, 2. And cofactor of 4, it is a plus, row and column is there, this one. It is adjoint A. It is adjoint A is nothing but it is a matrix. After transposing the elements replaced by its corresponding cofactors. That is for 1 we get 4, for 2 we get minus 3, here minus 2, here it is 1, but transpose. Don't forget. That is 4 minus 3 minus 2, 1. It is simply I will tell it then. But in the exam we have to follow this method. Suppose A is equal to A, B, C, D is there. Then adjoint A is nothing but the first diagonal, the elements are replaced, interchanged. In the second diagonal, it will the same element, but it is negative. If positive is there, plus is there, minus is there, plus, like this. That is adjoint. Okay na? So that is over. Now we are going to second one. Where given the matrix A is 1, 1, 2 and it is 2, 3, 5, it is 2, 0, 1. Okay now? Yeah. First we find the cofactors. Continue. Cofactor of 1 for this one. It is a plus, mind it. Always plus, minus, plus, minus, plus, minus, plus, minus, plus. You mind it now. For 1 the minor is deleting this one. 3 into 1, 3 minus 0. 3 by 0 is equal to plus 3. Similar cofactor of, again one more 1 is there. It is a minus of deleting a row and a column. We get these are the elements. That is 2 into 1 is 2 minus 10 is there. It is 8 plus 8 minus again minus is there. Cofactor of 2, you don't confuse. The plus 1 is a separate one. For the purpose of calculating finding the cofactors only. Don't confuse. For 2, I have to mention plus. A row and column is related. 2 into 0 is 0 minus 6. 0 minus 6 is equal to how much? Minus 6. Okay, na? Similarly, cofactor of 2. Cofactor of 2. This 2. Row and column is deleted. We get these are the elements. But it is mentioned with the minus. These are the elements. 1 into 1, 1 minus 0. That is minus 1. Cofactor of next 3 is there. Its sign is a plus. Row and column is deleted. We get these are the elements. 1 minus 4. 1 minus 4 is minus 3. Cofactor of 5. It is minus of row and column is deleted. We get 1 1 2 0. 0 minus 2. 0 minus 2. Okay, na? It is plus 2. Okay, na? Similarly, we will calculate for the third row. Okay, now cofactor of 2. Again 2 is there in the third row. Row, column deleted, we are having this one. 1 into 5, 5 minus 6. But plus is there. 5 minus 6. It is minus 1. Cofactor of 0. It is a minus of row, column is deleted. 1 into 5, 5 minus 4. 5 minus 4 is equal to minus 1 here also. Cofactor of 1, the last one. It is mentioned with the sign. Sign means plus or minus. Here it is plus 1. Plus 1 of 1 into 3. 3 minus 2. It is 1 plus 1. Okay, na? You verify one more time. Because when we are doing the arithmetics, be careful. 1 of 3 minus 0, 3. Minus 1 of 2 minus 10 is minus plus 8. For 2. 2 into 0, 0 minus 6 is minus 6. For 2, it is 1 minus 0. That is minus 1. And for 3, it is also 1 minus 4 is minus 3. For 5, it is 0 minus 2. It is plus 2. And for 2, 5 minus 6 minus 1. For 0, it is 5 minus 4 is minus 1. And it is 3 minus 2 is 1. Yeah. Now we need adjoint of A only. Adjoint of A is you replace the elements of the given matrix by its corresponding cofactors. That is, 1 is replaced by 3, 8, minus 6. And minus 1, minus 3, 2. And minus 1, 1. And transpose. Don't forget this transpose. Simply we replace the elements of the given matrix, okay, na, by corresponding cofactors. Now transpose it. The notation is there. That is 3, 8, minus 6. Minus 1, minus 3, 2. Minus 1, 1 is there. Okay, na? So this is adjoint of the given matrix 3 by 3 matrix. Okay, like this we have to prove. Okay, that is. And third one. Third one is verify A into adjoint A and adjoint A is equal to det A into I. First we find given. What is given? Capital A is equal to 2 by 2 matrix. 2, 3, 4, 6. So what is det A? First we find det A. Det A is the determinant of 2, 3, 4, 6. That is 2 into 6 minus 4 into 3. That is equal to 12 minus 12. It is 0. Okay, na? Determinant is 0. Well, it is a different type of problem. Now, what is cofactor of 2? Already we did like this problem. For 2 is plus, it is 6. Cofactor of 3, it is a minus 4. And the cofactor of 4, this 4, is also minus 3. For 4, 3 later. For 3, 4. Okay, now? And one more thing, cofactor of 6. What is cofactor of 6? Is 2, 1. So, what is adjoint of A for this? Adjoint of A is, you simply replace the cofactors. 6 or otherwise simply you may write it. Already I told you, it is 6, it is minus 3 and it is minus 4 and it is 2. Directly, without mentioning the transpose, directly I put the answer. Adjoint A, B, C, D. In the previous problem, A, B, C, D is there. In the first diagonal, elements are interchanged. Here, sign only. Plus 3 is there, minus 3. Plus 4 is there, minus 4. Okay, now, this is the thing. Now, A into adjoint A. Okay, now we are considering A into adjoint A. What is A? 2, 3, 4, 6. And what is adjoint A? 6 minus 3 minus 4, 2. And it is 2 into 6, 12 minus 12. Minus 6 plus 6. Multiplication right. 4 into 6, 24. Minus 6 into plus 6 into minus 4 minus 24. It is minus 12 plus 12. So we get 0, 0, 0, 0. Okay, na? 0, 0, 0, 0. So it is no doubt, it is 0. We may take as 0 as common. Okay, na? 1, 0, 0, 1. Can you write it as like that? 0 into 1 is 0, 0 into 0 is 0, 0 into 0 is 0, 0 into 1 is 0. And what is 0 in this case? That A is equal to 0 in this case, we know it well. That A is equal to 0. So here we may write that A into this is I. Will you agree? Like this. Similarly, we will prove adjoint of A into A. What is adjoint of A? 6 minus 3 minus 4, 2 na? And it is 2, 3, 4, 6. Okay na? Now, you observe. 6 into 2, 12 minus 3 into 4 minus 12. 6 into 8, 6 into 3 is 18 minus 3 into 6, 18. It is minus 8 plus 8. Here also minus 12 plus 12. Here also it is 0, 0, 0, 0. We may take 0 as common, and it is 1 0 0 1. Already we know what is 0 means is that here indeed is I. Therefore, we verified that it is verified. We verified that A into adjoint A is nothing but adjoint A into A is equal to that A into I. Okay, na? Like that, I will prove. Yeah.